about prospective and retrospective studies. So a prospective study, like a clinical trial, we're thinking about a 2x2 table, and we have some kind of treatment and control, and we have an outcome, maybe good and bad. And in a prospective study, we choose our treatment and control groups. So we split our population into two, or if we're doing something where we're observational, we're looking at smokers and non-smokers, we pick a bunch of smokers and a bunch of non-smokers out of the general population, and we follow them to see what happens to them, right? Do they get cancer or not, for example. And so let's say the treatment in this case would be smoker, and the control will be non-smoker, and let's change this around, cancer and healthy. And we have some numbers here, which is the counts we get. And the row totals, n1 plus and n2 plus, and the column totals, n plus 1, n plus 2. The idea is that in a prospective study, we're doing a product multinomial sampling on the rows, so we're fixing the row totals, and we get, in this case, a binomial sample. And so we're perfectly able to infer conditional probabilities, probability of cancer given treatment versus probability of cancer given control, right? And so we fix the rows, and we're allowed to infer things like probability of cancer given smoke, probability of health given smoke. But we can infer the columns. We can't infer things like what is the overall rate of cancer in the population, because we're not sampling from that fairly. We can't infer things like what is the overall rate of smoking, right? So we can infer, maybe we can infer cancer if we think about this as being just overall population, but we can't say something about what is the overall rate of smoking versus non-smoking because we fixed these two totals. We chose these in the beginning. And we certainly can't make an inference on total sample size, of course. And that's usually OK because we're not actually interested in those things, right? So that's an example of that is like this Framingham heart study, or a clinical trial is kind of the gold standard for establishing causality. And that's great, except that doing such a thing is usually expensive and requires that you can actually follow the patients or look at the outcome long enough to see what happens, if they develop cancer or not, right? So like the Framingham heart study is like a 30-year study, or 40-year now, or something like that. So you start, and it might take decades for it to resolve. So our final observation last time was that we can think about a retrospective study, which means that we're fixing the groups on top, and then so we're fixing the columns, or we're fixing the outcomes, and then we're looking back at among those groups who were smokers and non-smokers, and there are some inferences we can and we cannot make in that case. So our observation last time was that the odds ratio, theta hat, n11, n22, over n12, n21. So that's the sort of cross ratio of probabilities. Is actually the same, whether it's prospective and I fix the columns of rows, or it's retrospective and I fix the column totals. So I claimed that was the same. I didn't show you why, so let me just do the calculation. So and I'll do it in terms of probability for this table. So we're saying that this odds ratio, so the true odds ratio, is the probability of smoking and cancer. And I might reverse the order of these two things. It doesn't. So just think of these as being two events. probability healthy non-cancer. So it's this one times this one divided by this one times that one, right? Divided by probability of non-smoking cancer, probability of smoking healthy. And we'd like to show that we can get this as either odds ratio. So this is probability of smoking cancer divided by probability of cancer, probability healthy normal, divided by probability of healthy. So this is just these two. And then I'm going to multiply by 1 over PC, 1 over PC. So probability non-smoking cancer divided by PC. So I just multiply by 1 here, 1 over PC over 1 over PC. And probability smoking healthy divided by probability healthy. So, okay, so I haven't done anything. I just multiplied by 1. But now these, by Bayes' rule, probability of smoking and cancer divided by probability of cancer is probability of smoking given cancer. So I can rewrite that as probability of S given C, probability of N given H, over probability of N given C, probability of S given H, right? Just by Bayes' rule. And then these are conditional probabilities and they have to sum to 1, so I can replace some of them with 1 minus the other thing. So this is probability of smoking giving cancer over 1 minus probability of smoking giving cancer. Just replacing that times probability of, let's do it the other way. 1 minus probability of smoking given healthy. That's probability of N given healthy is equal to 1 minus probability of smoking given healthy over probability of smoking given healthy. And then I can slightly rearrange that to get probability of smoking given cancer divided by 1 minus probability of smoking given cancer over probability of smoking given healthy divided by 1 minus probability of smoking given healthy. Okay, so that's the odds ratio. Which odds ratio is that? The prospective or retrospective odds ratio. Have I conditioned on the rows or the columns or the treatment or the outcome? Compares these two. So this is a retrospective odds rate. This is computed retrospectively. And if I go the other way, so I take this same quantity, I can say that it's equal to probability of smoking and probability healthy normal, probability normal cancer, or non-smoking cancer, probability smoking healthy, and I'm going to divide by PS and PS, and divide here by Pn and Pn. So now I'm going to divide by the total, or the proportions of non-smokers and proportions of smokers instead of over here, the columns. And so what I'm going to work toward here is the prospective version. So using Bayes' rule, that's probability of cancer given smoking, probability of healthy given non-smoking, divided by probability of cancer given non-smoking, probability of healthy given smoking. And then using the fact that the conditional probabilities are 1 minus their complement, I can rewrite that as probability of cancer given smoking times 1 minus probability of cancer given non-smoking over probability of smoking given healthy times, that's not what I want. Smoking given cancer given non-smoker times 1 minus probability of cancer given smoker. And then that's an odds ratio for the prospective study. 1 minus probability cancer given smoking divided by probability cancer given non-smoking over 1 minus probability cancer given non-smoking. Okay, so that's the prospective. Okay, so if you didn't believe me those were equal, that shows you those are equal. And I'll remind you that we get, for either of these, since they're the same, we get our nice MLE that couldn't be simpler with estimated variance V of log theta hat, which is just 1 over the sums. So you take the square root of that, multiply it by 1.96, add it to log theta hat to get a confidence interval, and then back transform to get your confidence interval for odds ratio. So odds ratio, as we said, is a little bit hard to interpret. So let me say a little bit about one way to interpret odds ratios. So there's a lot of different tricks you can use. One is that we'll see when odds ratios, or when the overall prevalence is very small, the odds ratio is very close to the relative risk. Let me give you at least one way to interpret what an odds ratio means. So if you can imagine, so odds again comes from sort of the idea of betting, or bet that someone's willing to take. So imagine that you wanted to bet on like the presidential election or on some other outcome, whether it's going to rain today, and you had two different pools to choose from of bettors, two different markets. So we have an event E, and we have market A and market B, and implicitly market A assigns probability P to the event, and market B assigns probability Q, and let's say probability P is greater than Q. Right? So that means that the odds in market A will be worse than the odds in market B. Right? A will pay you less if E happens than B will pay you. Right? So if you imagine this is like, you're betting on whether Trump is elected president. If market A thinks it's less likely, this is the Democrats and this is the Republicans or something. So if the Democrats market thinks or the Republicans market thinks it's more likely, they're going to pay off less. Maybe they'll pay 2 to 1, and the Democrats will pay 3 to 1 or something. Right? Okay, so in A, the odds ratio is P over 1 minus P. So if we bet $1 on E, so if E happens, I get some money. If E doesn't happen, then I have to pay $1. Pay later. My payoff is some number X. So, or let's call it, what's a good letter for payoff? Let's just call it X. Okay. So X is the payoff if E happens in market A. And if with probability 1 minus P, I lose $1. Right? So with probability P, I get X. With probability 1 minus P, I lose X if I bet in market A. And if that bet is fair, from the point of view of A, that expectation should be 0. Otherwise, the odds would move. So from the point of view of that market, that should be 0. And so just algebraically, that means that Px equals 1 minus P, or X is just the reciprocal. Right? So the payoff for A is 1 minus P over P. So that's the payoff that has to be for A to be sort of fair, or to represent this belief. For B, for the same logic, let's say the payoff for B is Q, 1 minus Q over Q. If E happens. And so P being greater than Q, of course, means that AB, of course, means that X has to pay less than Y, because the people in market A think that the event is more likely Right? So they're willing to pay you less for it. Okay, so if that really happened, right, there was two markets, you could make an arbitrage. You could make a riskless profit, right? There's a trick you could do such that you would never lose money, but you sometimes would make money. What's that trick? If you're allowed to take either side of the bet in both markets. Do you know the answer? Nodding. What would you do if that was really the case? Right? There was two groups on campus. One was offering odds P, and one was offering odds Q, or P over X and Y, and this probability was greater than that probability. What would you, how could you be sure to make money, or at least not lose money, and possibly make money?
I'd split my investment between both groups.
Right. Well, there's something you can do that's even better, right? Which is that I can bet that E will happen in the market that pays more for E. So I bet E will happen in market B, and I bet not E will happen in market A. If not E happens, I pay one $1, they pay me $1. If E happens, I get Y from B, and I owe X from A, right? So I make money because Y is bigger than X. So if I take the opposite sides of the bets, I make money. How much money do I make? For every $1 I invest, I make Y over X. Right? So that's what the odds ratio is. And one way to think about what the odds ratio is that if, so this is 2, say, or let's say in a concrete example, P is equal to 1/2, Q is equal to 1/3. So this is 1-to-1 odds, and this is 2-to-1 odds. Y over X is going to be 2. So that means for every $1 I invest, if E happens, I get $2. I double my money. If E does not happen, nothing happens. I don't change my bets wash out. So that's one way to think about what odds ratios mean. I mean, that's not so great for thinking about clinical trials, but at least it's a number, so it's not just an arbitrary number that doesn't connect to any possible event. Okay, so in these sort of prospective, retrospective situation, in the retrospective situation, the odds ratio is all we get. We don't get to get relative risk. But if the PIJs, if the conditional probabilities are small, these are close. These are close. The odds ratio, so they weren't small here, is close to relative risk. So the odds ratio is equal to the relative risk times 1 minus probability of 2 given 2 over 1 minus probability of 1 given 2. So for example, okay, so suppose the event that I'm interested in, so I'm thinking about flying on 2 different airlines. I have a choice between drunken airlines and responsible airlines. Okay, and I have some probability of crashing. Probability of crashing on drunken is 0.001, and probability of crashing on responsible is 0.0001. Right? So wildly different, but not that bad either way. So the difference of proportions is 0.0009, which is sort of hard to interpret, but there's one nice way to interpret that, which I'll talk about in a second. There's probability of X given D divided by probability of X given R. That's how much more likely am I to die on a drunken airline's flight versus a responsible airline flight. I'm 10 times more likely. Right? And the odds ratio, so you plug it in to either that formula or just the usual formula. So the odds ratio is 10.009, which is approximately, I think there's some more digits there, probability of X given D, so the relative risk times 1 minus 0.0001 over 1 minus 0.001. So this thing, 1 minus the chance of dying unresponsible, 1 minus the chance of dying on drunken, that ratio is close to 1 because these numbers are very small, so they don't change the relative risk very much. And this number, the odds ratio, is very close to the relative risk. Okay, so this tells you that, okay, it's bad news that in a retrospective study you only get odds ratios, but as long as you're studying something that's very rare, it sort of doesn't matter. It's going to be very close. Okay, so if you're looking at a population, you're studying some rare disease that hardly anyone gets, and you're looking for risk factors of it, then your odds ratio is going to be just as good as your relative risk, pretty much. Okay, but if we're in a more common situation, like, hey, these airlines are really bad, and probability of drunken crashing is 0.3, and probability of responsible crashing is 0.15. So the difference in proportions is 0.15, and the relative risk is 2. The odds ratio is actually going to be 2.43. So it's significantly different, in the statistical sense, but okay, it's very much not 2. Right? And this is one reason why, right, like people like to respond, like if this was a journalist article, this was a news article, they wouldn't report this number. You know, they might report this number, and they might really like to report this number because it sounds the most extreme, right? But it's, again, hard to interpret unless you think about gambling on it or something, being an insurer. Okay, so that's equal to the relative risk times this ratio 1 minus px given d. And here this is now going to be 0.85 over 0.7, which is different enough from 1 to multiply 2 up to 0.43. Okay. So I want to make one other comment while I'm talking about this. So this number here, the difference in proportions we were sort of critical of. So it turns out that this thing, which is sometimes also called the absolute relative risk, I think. No, absolute, something like absolute risk. Anyway, whatever it is. So this number, the difference in proportions, people like to use this. There's an interpretable version of this, which is if you take its reciprocal, so 1 over this number, people call 1 over delta is called the NNT so in clinical trials, or when you talk to people who are thinking about medical treatments, and this is an estimate of the number of people you would need to treat in order to see one difference. So in other words, if you're thinking about it as like you have a treatment like the vitamin C versus cold, this number would be the number of skiers that would have to give vitamin C in order to see one person that didn't get a cold, to expect that we wouldn't get a cold. So people like this because it gives you a sense of the magnitude of the number of people who and their side effects and everything else that you would have to deal with, and it allows you to compare lots of different studies just on, do I need to treat 1,000 people to get this effect? Do I need to treat 10 people to save one? And obviously you also think about what the effect is, right? Is the outcome that they die? Is the outcome that they don't get a cold? And weigh that against the cost of that treatment. So that's a popular number as well. So how would you compute a confidence interval for this, by the way? The number of NNT. The number you need to treat.
I mean, if you just do a paired t-test on
yeah, that's the basic idea, right? So we argued that this thing was normal with some variance. Okay, so that may or may not be a good approximation depending on various things, but we certainly argue that we should think of this difference as being normally distributed. So what is 1 over a normal? Okay, that's kind of ugly. Let's not think about that. Instead, what we can just do is say, construct a confidence interval that you like somehow here for this difference based on a normal approximation, and then just treat this as a transformation. So you're interested in this number, but it's poorly behaved potentially, so you transform it by taking its reciprocal. You get something which is normal with a variance you understand. And then you construct your confidence interval and you back transform it. All right? So that works fine as long as if this confidence interval contains 0, or is sometimes negative, then some weird things happen here, right? But that just means that what's going on is that if it contains 0 or it contains some negative numbers, it means that the treatment that you're giving people might actually hurt, right? Or might not benefit them at all. And so this number, so in order to treat, if it's worthless, as an approach, the treatment approach is worthlessness, this number goes to infinity, right? As this goes to 0. So it means, I need to treat 100,000 people, I need to treat 1 million people, I need to treat infinitely many people before I see any benefit. And then when it gets past infinity, it rolls over to negative, right? Which means at that point, you're saying it's actually harmful. Right? So people would report this as like, they might say something like, oh, you have to treat -4 people, meaning it's actually harming them, which is just a way of saying this difference is in the other direction. Right? So this is sort of bad when you think about something that contains, if this thing contains 0. But if this doesn't contain 0, the confidence interval, this makes perfect sense. And people very much like that as a single number to summarize effects for clinical. So the next topic is extending the logic for 2x2 tables to larger tables. What can we look at? We can look at residuals in exactly the same way, like a Pearson residual. Right. We know how to calculate EIJ and OIJ from, well, OIJ, sorry, that's not beta, that's O, from the marginals if we're testing against independence. And these Rij are going to be approximately normal. I promised I would say a few words more about the statistical treatment of residuals. So they're going to be approximately normal, and the mean is going to be 0. But if you think about it, the variances kind of depend on the multinomial, so the variances are not all equal. What we can say is that the average variance, I minus 1, j minus 1, divided by number of cells, because that's what we expect from the chi-squared. And so, okay, so the average variance should be 1 or so, a little bit less than 1. And we can adjust for the this fact that the variance is not all equal to get a standard deviate for each of the residuals. So we just want to divide by what we expect the variance to be, 1 plus p I plus 1 minus p plus j. And this thing will be approximately normal with variance 1. And that's where this kind of rule of thumb of 2, so if this, you can't calculate this number and it's more than 2 or 3, then you're comparing against a normal table. Right? 2 would be sort of a 1.96 would be sort of a 0.05 level, but then there's this multiple hypothesis testing if you have many of these cells that you have to worry about. So you can use a rule of thumb, or you can so the rule of thumb is like 2 or 3. This is bigger than 2 or 3. That's sort of an interesting thing. Another way to think about it is that when you compute these standardized residuals for the whole table, it's telling you which cells in the table are really the ones responsible for pushing you away from independence. Right? Which cells defeat independence. And it could be that that responsibility is shared among the cells, but if it's localized in a few cells, that could tell you a lot about your data. Right? That's where the effect happens. And maybe you should zoom in, or maybe you should collapse parts of the table that aren't interesting. Okay, but let's move on to think about how to deal with these other measures like odds ratio, difference in proportions, and relative risk for these bigger tables. Okay, so now we have some bigger table, let's say 2 by something, 2 by 4. And it can fail to be independent. Right? We can perform a chi-squared test on it. We get some number of degrees of freedom. Right? We get I minus 1, j minus 1 degrees of freedom, which is how many here? 4 minus 1 times 2 minus 1, 3. So we get 3 degrees of freedom. So what does that mean? It means that there's sort of a 3-dimensional departure from independence. So that's a little bit weird, right? So the first thing you might think is, okay, well, I have a bunch of entries in this table, and I can compute the odds ratio, the difference proportion, the relative risk for any 2 by 2 subtable. Right? I can go this versus this times this, divided by that times that for the odds ratio, this times this, divided by that, and so on. And I can choose 2, I have no choice here, and I have 4 choose 2, which is 6 choices here, right? So there are 6 possible 2 by 2 tables. To consider, but there are only 3 degrees of freedom. What that's telling us is that these 2 by 2 tables aren't independent. If I know 3 of them, I know the other 3. I can compute them by adding and multiplying as appropriate. And so that means that sort of, unfortunately, you have kind of a choice that you have to make as to which ones you want to use to represent the differences. That's like choosing a parameterization of this probability distribution. So for example, I could say, well, I'm going to compare these 2, and I'm going to compare these 2, and I'm going to compare these 2. First versus second, first versus third, first versus last. That would be perfectly reasonable. Or I could compare first versus second, second versus third, and third versus fourth. Or I could choose something else. So for each of those, I'm going to get an odds ratio, or a difference in proportions, or relative risk. And for those numbers, I can compute the rest. Okay.
So the number you choose to compare is the degree of freedom?
So I get 3 degrees of freedom. I get 3 parameters to describe my departure from independence.
Okay.
One possibly helpful, possibly not helpful way. So in your homework, there was this problem to draw the independent surface. Right? And when you have a point that's not on the independent surface, if you think about something like n11, n22 over n21, n12 equals theta. So on the independent surface, of course, n11, n22 minus n21, n12 is equal to 0. At your point with some odds ratio, what happens is that n11, n22 minus theta n21, n12 is equal to 0. So if you want to picture that surface, what happens is I change theta is it deforms that surface. So it like stretches it up or stretches it down, and the odds ratio in a very one-dimensional way. Right? It's a big surface, but it's only being stretched in a one-dimensional way with one parameter of deformation. That how far you have to deform it is the odds ratio that you get. So and then in a higher dimensional case, we just have to have more parameters that we get to use to deform our surface. But not infinitely, not 6 parameters, we only get 3 parameters. So let's do an example of this phenomenon from your notes. Which is the heart disease version. So this is a coronary heart disease from the Framingham study. And our outcomes are either we get this disease, or we don't get the disease. I have a total. And the treatments, our cholesterol, well, they're not treatments, but this is prospective, so they actually followed all these people. 0 to 199, cholesterol levels. This is cholesterol. 0 to 199, 200 to 219, 220 to 259, and 260 or more higher, and then total. Apologize for my poor drawing here. 12, 8, 31, 41, 92, 1237, 245, 439, 246, 307, and down here the totals 319, 254, 470, 286, 1329. Okay. So we have a binary variable and then a 4 outcome thing. And this was actually, it was continuous to begin with, but it was grouped. So now it's become interval or ordinal data. And so now we'll see an example of that. So one way in which we can work in the ordinal or interval nature of it is in our choice of comparisons, right? So either of these choices of comparisons is very consistent with the idea that this is an ordinal variable, right? Because we're measuring at each stage either how much do each of these cholesterol levels increase your risk over baseline, if we believe that the risk goes up with cholesterol, or we can say as I go from this class to this class, this class to this class, this class to this class, how much does it increase my risk, right, at each stage? So I could compute the proportions. Let me just back something on the table. CHD, no CHD. So this would be 0.038, 0.962. So these are things that sum to 1. 0.031, 0.969. 0.066, 0.934, 0.143, 0.857. And so the kind of tests we might do is, all right, we want to know, for example, whether this is increasing. Right? As I go from this proportion, 0.038 of them got disease in this level, 0.031 got disease in this level. Okay, so it looks like it's actually better to have more cholesterol. Maybe it is. We could test, is it better to have more cholesterol at this level, and is it significant? And we could separately test, is this jump, this is apparent doubling in the rate of disease from 0.31 to 0.66, the doubling in the relative risk being around 2. Is that significant or not? Is this again doubling or more here? Is that significant or not? Or we could ask in terms of odds ratios or proportional risk or a number needed to treat or whatever. So in other words, what we want to do is take subtables of that. But it's just that they're not all free, right? Only 3 subtables are free, and then the other 3 subtables are fixed. So, for example, if we zoom in to the subtable comparing the first 2, 0 to 199 and 200 to 219, then and we could just do a Pearson test. And we get an x squared of 0.157. There's only 1 degree of freedom because we're just looking at this 2 by 2 table. And so the p-value is 0.69. So that tells us that the first comparison that we want to do of these first 2 columns, while it seems that the risk decreases as measured by proportional difference, odds ratio, relative risk, that decrease in risk is not significant. Okay? So we might even say that was evidence that we should be allowed to combine these two tables, or these two columns. Right? So this is not really any different, and we should just combine them into 0 to 219, for example. That's one conclusion we could make from that. And then we could go on and do a separate test for the second two, and it would be significant, and a separate test for these two, and it would end up being significant. Okay. So does that make sense? The kind of tests that you would need to do in the sense of relative risk. Let me do a second example. The smoking one. The smoking students yes or no, and number of parents that smoke, either both, one, or neither. So obviously we have some ordinal or data going on here. And the outcomes were this. And we have estimates probability student smokes given that both parents smoke is 0.225. Probability student smokes given that one smokes is 0.0186. 0.186. And probability student smokes given neither smokes is 0.139. And we're interested in comparing these two and these two, say, or we could compare, that would be like the pairwise sort of adjacent approach, or we could compare this versus like no smokes versus one smokes, and no smokes versus both smokes. And we can ask other questions like, well, given that at least one parent smokes, does it matter whether it's one or two? So those are the sorts of questions we can answer. So let me see. So these numbers, this is difference in proportions 1, 2, difference in proportions 2, 3. D2, 3 is 0.047, and D1, 2 is 0.039. Obviously, if I tell you this difference and this difference, you can compute that difference, right? So that's a very easy way to see why we lose a degree of freedom. Just add them together. The other ones sometimes are a little bit more subtle if we want to do it in terms of odds ratios or something. So like theta 2, 3 is 1.42. Theta 1, 3 is 1.80. And from that, you could get theta 1, 2. So the next question I want to answer about these sorts of tables has to do with the result of collapsing them. And so in this setup, what we're going to use is a statistic like the deviance or the Pearson statistic, and we want to break up this into kind of like an analysis of variance where we ask how much of this failure of independence is due to different collapses of the table, or different ways of breaking it up into sub-collapses. So, for example, in this one, I could say, does the student smoke yes or no, and I can group these two rows into at least one parent and 0 parents smoke, and get the totals. 816, 188, 3203, 1168. And then I can compute a g squared for this, which happens to be 29.1, and the p-value is very close to 0. And I get some odds ratio. Okay, so students are more likely to smoke if at least one parent smokes. And then we can ask separately, given the part that I collapsed, given that at least one parent smokes, so given that I'm in this collapsed part here, does the additional parent smoking make a difference? So now I ignore this one because I've already treated it once, and I take the collapsed one, break it up, and look at the cells individually. So I'm just looking now at that one column broken up, 400, 416, 1380, 1823, and now our g squared is 9.2, and I have some odds ratio which is not as strong as the other one. So this says, okay, and p-value 0.002. So in this case, what it tells us is that the most important thing is whether or not they have any parents that smoke that has a strong effect and a very high significance. Given that at least one smokes, whether one or two does, is still significant, though not quite as strong, and it still has an effect, though not quite as strong an effect. Okay, so it sort of partitions. You could imagine a situation where, if I failed on significance or my effect was low here, I could conclude, well, it doesn't really matter whether it's one or two, and I'm perfectly fine to collapse these cells in my study, because it doesn't give me any additional information. And the other thing to notice is that, or the reason that this is nice is that because I did this kind of hierarchically, 29.1 plus 9.2 is 38.3, and with significance, it's 38.4, which is the g squared of the overall table. So if I had done the g squared here, I would get 38.4. So the deviant statistic, when I do a partitioning like this or a hierarchical collapse, will exactly sum up to the total. The Pearson statistic will approximately sum up to the total. So this is a nice way to sort of take your table and break up your effect or your departure from independence into the different sub-effects, and be able to say something about the significance and the effect size for each of those. Okay, last topic for today is exact tests. So the classic example for this is the lady testing T. You've already had one of these on your homework, the handwriting expert. Let's just quickly talk about it. So the idea is that there was a lady who said that she could determine whether when someone made tea, whether the milk was poured first or whether tea was poured first, just by tasting it, in terms of, I don't know how much the milk got cooked. So we have first either tea or milk, and the lady thought it was either tea or milk. And this is going to be both rows and column are fixed. That is, we poured the same number of cups. We poured 8 cups, 4 tea, 4 milk, and we told her it was 4 tea, 4 milk. So we fixed the row and column totals, so we have a hypergeometric sampling. And the outcome looked like that. So hey, she was pretty good. So the null hypothesis is that she can't tell. And that would say that the cups that she drew as tea first were a random sample. The ones that she drew at milk first were a random sample. So the probability, once I fix one cell, because all the row and column totals are fixed, once I fix one cell, I can determine the rest of the cells. So all I have to do is compute the probability of number of black balls drawn from the urn. So the probability that n11 is equal to 3 is given by hypergeometric. Which is 0.229. And then for our p-value, right, we want how likely is it, if the null hypothesis is true, that something at least as extreme as what we observed happened. Right? That's what the p-value is. So that means that the only other table to consider, so that means that we have to look at the space of all possible tables. Which table will give us a more extreme result? And the thing we're interested in, the thing we're interested in is n11. So in the space of all possible tables with these marginals, the only more extreme one is if this was 4. Right, so the only more extreme table has n11 equal to 4. So that's this table. That she predicted it perfectly. And that one has probability equal to 0.014. And so our p-value is 0.229 plus 0.014, which is not very small. And so we didn't have enough evidence to show that she could do it, although, turns out she could do it. She did the experiment 4 times. So this says we don't have enough evidence to reject the null hypothesis. The other thing so some software will default to doing an exact test in the cases where it's warranted. So if you have too many cells with small probabilities, you have a small sample size, your normal approximation is going to break down. Some software will default to it. In some cases, you want to choose to do it deliberately. And there's an extent to which these tests are too conservative in the sense that the probability of an incorrect rejection of the null is smaller than you want it to be. So if you try to get it to be, if you set your cutoff to 0.05, because of the discreteness, it will reject the null too rarely. Right.